Welcome, everyone, and happy Halloween. My name is Michelle Branzaleski. I'm the marketing manager here at Control Station. Um, we are just going to wait a few minutes. We have a really big sign up group for today, and I see a lot of people still kind of popping in. So if you can bear with us for just a minute or two, I want to give everyone the chance to get on. Thank you. Okay. Again, welcome everyone. My name is Michelle Branzaleski. I'm the marketing manager here at Control Station. Happy Halloween, and thank you for your privilege of joining us today. Today's topic, Process Control 101. And what we're going to do is put your knowledge to the test today. So with that, let's get our presentation started. With me today, I have my colleagues, Brett Beauregard, Director of Product Development. Brett, good morning.
Morning, Michelle. Morning, everybody.
And also, we have one of our North America sales managers, Brian Coughlin. Good morning, Brian.
Morning, Michelle. Morning, everybody. Thanks for joining us today.
Perfect. So what I'm going to do is cover a few things about Control Station if you're not familiar with us. So here at Control Station, we like to partner with our customers to solve their process control needs using a combination of world-class software and expert services. We have offices in the United States and Ireland and have successfully deployed our solutions to support facilities located in over 70 countries, and this is still growing. We are proud to partner with 1 out of 2 manufacturers that are listed in the Fortune 500. We also have been around since 1998 and was founded on the campus of the University of Connecticut. So with that, I'm going to hand it over to Mr. Coughlin. Brian.
Yeah, so thanks. So today we were going to talk about some of the challenges or some of the what's at stake with poor control. Poor control costs process manufacturers millions of dollars every year. I'm sure it's something that you've been dealing with. It's also a time and an effort drain on your teams and your processes. When control of critical production processes is variable, it wastes energy and production inputs, quality slips, and safety is compromised. Production slows, confidence lags, and work orders start getting generated, and we want to avoid that if we can. They hit your top line in the form of reduced throughput, as well as erode bottom line in the guise of production-related defects. So Brett's on the phone with us today, and I was going to ask him, since he deals with this a lot more than I do, if he has anything to add as far as how that goes and how much poor PID control can really hamper production itself.
Sure. I'd be happy to answer that, Brian. So there has been a decent amount of study on this. And so, for example, this is now relatively old, maybe 20 years ago, there was a UK-based study that talked about the economic effects of poor control. And this is kind of what we saw, or what was seen, that there was a decrease in throughput and yield of 2 to 5%. There was an increase in energy consumption and product defects. Again, this is a relatively old study, but we have seen these effects come to bear time and again in different processes. Just so you know, the study was called Invest in Control, Payback in Profit. So basically, studying a variety of production plants, they were able to determine that these were pretty much industry standard things. And we've, as I said, we've seen this anecdotally throughout our many years of experience with production plants. Ooh. As I try to get to the next slide. Oy, my pointer is trapped. Just what I wanted to have happen right now. What is there we go. Okay, good. Whew. So as I mentioned, we have seen these even when a plant is in automatic mode, still is not going to be operating at its most efficiently 85% of the time generally, as found. This is what we found. When you have control related problems or you have valve related problems, we find that sometimes controllers are tuned poorly to mask those problems. Perhaps you have a sticky valve and you've decided to detune the controller to make that happen. There are many situations in which the control loops are operated in manual mode, 30% depending on the site, and also depending on the time, depending on the operator. We find that many loops are operated in manual mode. And just in general, just because a loop is tuned for a certain tuned to look good, that might not actually meet the total objective. For example, a surge tank might be tuned to have a perfectly flat level. Now, while that level might look awesome, it is not very well tuned. Ultimately, all of those things, when it comes, maybe not the manual one, but when it comes to loose control costing money, it all really kind of comes down to this plot. So this is a very common visual that people have seen, this part on the left here, where a poorly tuned loop is okay. It's safe, at least, right? It's held within control and everything's fine. But generally what happens is for all of these things, for yield and for energy use and for variability and all of these things, generally the most profitable place to run is near a constraint. If you're trying to remove an impurity, you don't want to remove more than you have to, but you need to be below the constraint. Or for throughput through a plant, perhaps you want to be pushing as much through the plant as possible, but you don't want to cross. So if you have variability in your process, on average, you're going to need to be operating at a certain distance away. But if you can reduce the variability, improve your control, then what you can do is on average, you can move more closer to this constraint, whatever that constraint may be. Just having better control gives you more options and more safety, all these great things that we've come to kind of recognize as the benefits of good control. So I'm going to pass this to Michelle for our first test your knowledge question.
Thanks, Brett. Okay, in a minute you should see the question on your screen, and I'll read it for you because I had to take some of the words out because they all didn't fit. So you get the full effects of the question and all the information. All you have to do is take your mouse and select the one that you think is the correct response. Controllers are designed and tuned based on the dynamic behavior of a process. What is meant by dynamic behavior of a process? Is it the first one, how the measured process variable responds over time to changes in the controller output and disturbance variable? Second one, how the controller output responds over time to changes to set point and tuning values? Or the third one, how the measurement filter removes random error from the measured process variable signal over time. So I will leave this up for a few, about another 30 seconds and give you time to respond to this. With that, I'm going to do a quick plug. Our next webinar in our public webinar series will be November 14th. And this is going to cover detecting mechanical issues in your plant. So look for an email from me on that, or go to the website and you can sign up early. All right. We got about 76. And so I'm going to close this. I'm going to share the results. So most of you picked the process variable response to CO and disturbance value. And if you did, you are correct. Ding, ding, ding. Halloween treat for you. So thank you for participating. I'm going to hide this and hand this back off to Brian. Brian.
Yeah, so thanks, Michelle, and thanks, Brett, so far. So Brett, as far as like a process control 101 goes, what does dynamic process behavior have to do with the PID itself? Or what's the real world advantages that can be expected when there's a better understanding of dynamic process behavior for our friends on the phone today?
So first, let me talk about the results there. So completely understandable that some people would be talking about how the controller behaves, because in general, when people think of the process, they think of the whole kind of thing. They think of the whatever is being controlled and the controller. So completely understandable interpretation of the question. But as we describe it here, the understanding the process itself before there's any control connected to it is what we're talking about when we talk about dynamic process behavior. And as we'll see, it's very beneficial when we're trying to understand what's going on or how we're going to control a given control loop. So when we're talking about dynamic process behavior, we're talking about a process, perhaps something like a cruise control in a car, okay? So the cruise control in the car is actually similar to the process that some of the respondents talked about, where we have a controller that's controlling a car. The cruise control idea is the same. We're trying to control the velocity or the speed of the car and based on some given set point, but the car that we're connected to is different. Now, if I see cruise control on an F1 race car, that would be pretty funny, but that's the idea. The cruise control algorithm might be the same, but the car that it's connected to will be different. So when we talk about dynamic process behavior, what we are talking about is how a controller output or how a signal going into a process will then affect what comes back to us, to the controller. That's the process behavior. The control loop is a process and a controller together. So the controller will send something out. In this case, it might be the gas flow to the vehicle. And then we have the response coming back. And the reason that it is called the dynamic behavior is because we're talking about how it behaves over time. You make a change, either a step change or a dynamic change in the gas flow, and there is a measurable time-based impact to the process. But also there are disturbance impacts. So even if we are sitting there constant, we will see if we go up a hill or if we see some sort of wind or things like that, we will also see dynamic impacts from those things. When it comes to control of a process, we are talking about how the controller output, when we're talking about the dynamic process behavior, we're talking about how the controller output affects the controller input, independent of whether the controller is on or any of those other things. So the way we understand this process is, we can look at it and we can get a feel for these things. But what we've come to find out is for accurate and precise controller tuning, what you want to do is bring math into the equation, so to speak. You can look at it and you can adjust parameters until the end of the day, or until the end of your shift, until the end of the week, until the end of your life. But what we've decided and what we've come to realize is that by bringing to bear a procedural mathematical approach, you can get good tunings early on. Okay, and the first step in that process is modeling or analyzing the process. Okay, so we, in this case, do a test of some kind, and we'll talk a little bit about tests in a little bit, but you want to make a change in the process. Maybe you step the valve closed, maybe you ramp up or you step up the VFD, you make a significant change, and then you observe the response of the process. Okay, you observe the response in a different, in whatever location you happen to be working with. If you have a furnace that normally operates at 800 degrees, you would want to do your testing or your understanding at 800 degrees. In the same way that a car behaves differently at 10 miles an hour versus 60 miles an hour, same as with most loops or most processes, you need to be doing your testing at a given design level of operation, as we call it. After you do a test, there are a variety of ways to analyze that data. The way that we have found for normal, what we call self-regulating processes, like most temperatures and flows and pressures and things like that, is to analyze it using this first order plus dead time equation. So this is an equation that has a similar shape to standard processes. It has a process gain, time constant, and dead time. These are variable parameters that will adjust the shape bigger and smaller to let us kind of fit it on top of our data. Depending on the test you do, you can fit this information graphically, or you can use software to extract these parameters. It is a relatively simple equation. But so is the PID algorithm, and so it winds up being a good match. It is a low order linear differential equation, and the PID algorithm is the same. So it works out well for getting the information that we need. So as I said, when you fit this to a process, you extract 3 model parameters that then unlock the understanding that we need to get good PID tuning parameters, regardless of the process. It could be a pH loop, it could be a temperature loop. Any loop that has this self-regulating shape will have some steady state process gain, which is an idea of the magnitude. When I step the output, how far does the process go? Does it go 5 degrees? Does it go -2 PSI? What happens when I step the output? It has a time constant, so it has a measurable change. Does it take 30 seconds to get to a certain spot? Does it take 3 hours? Does it take 6 seconds? Whatever. The time constant gives us an estimate of that. And then it also has a dead time. So all real world processes have an apparent dead time where you make a change and then you wait and you wait. And sometimes you wait a little bit more. And then, oh, there it is. Okay, so it takes time for the process for whatever change to percolate or process through the system before you finally see a response. Okay, so those are the different parameters that you can get by analyzing. Once you have that information, then tuning becomes a much easier, almost trivial process. So that is dynamic behavior and a relatively straightforward way to understand that behavior. So I'm going to pass it back to Michelle here for the next question in our test to test your knowledge.
Okay, thanks, Brett. All right. Same deal as last time. You should see it on your screen in a minute or two. Again, take your mouse, click which one you think applies. Which industry collects the most data? Is it financial banking industry? Is it the government? Manufacturing? Retail? All right. I'll give you some time to select, make your choice. Then I'll share the results. Okay, a few more seconds. Looks like we got almost 100% of the vote in. right, I'm gonna close it down and I'll share the results. All right, so 15% think it's financial industries, 10% the government, 68% says manufacturing, and 8% says retail. All right, Mr. Coughlin, do you want to give him the correct answer, please?
Yeah, I believe that answer would be manufacturing, Michelle. Correct me if I'm wrong.
No, you are correct. We just need the next slide, please. There we go.
There we go. Yeah, so this kind of brings me to another topic I was going to, bring up, which is, one of the things I do for Control Station is go around, talk to different customers and different industries across different, locations, geographies, things along those lines. One of the conversations that we keep having is the growing mountains and mountains of data that customers and prospects are dealing with. Brett, it kind of sounded like you were talking about step tests and bump tests a little bit ago as far as data goes, but that's not all that constitutes good or bad data. What is it that you're looking for in data? What makes good data good, bad data bad, and how does that affect what's going on with the PIDs?
Yeah, let's talk about that. So yes, as I mentioned, there are a variety of different ways that you can move the process around, but not all data is created equal. So when we're trying to analyze the process, we want to see the dynamic behavior of the process. Back to our cruise control in a car example, if you are sitting at a if you're very, very slowly creeping up your speed, for example, as in this case, where we make a set point change in our cruise control, but for whatever reason, the gas pedal is just moving very, very slow. Now, of course, this is a reverse acting process, so this would not be what would happen in a car. But as you are backing down slowly, we don't know for a fact that this is dynamic information. We could be moving through a series of steady states, similar to the situation where maybe in manual mode, we are slowly ramping up the output and we are observing a steady decline. This is not good data for a test. We want to see a sharp controller output step. It does not have to be a full step as in this case, but we want to see a sudden controller output change. In this case, they're saying 3%. I would say case by case, 3% is a rule of thumb, but if you have a very noisy process or something like that, that might change the equation. You might need to make it a little bit bigger, but make a sudden change so that we can be clear, yes, we made this change. Here is the dynamic response, and then we can go ahead and analyze. So here we can see, so this is a perfect example of this third point. So when you're doing a closed loop or automatic mode test, that's really when you have to be careful about this sharp controller output thing. If you're doing it a manual mode test, as long as you're not doing a ramp, if you're just stepping the output, you're good. Okay, that's a fine test. But if the controller is very conservatively tuned, you can get into a situation like this one where the output is moving so slowly that we can't be sure that we are seeing a real change. But for the most part, a standard tuning of a controller, even if it's a poorly tuned controller, as this one is very aggressive, will give you the dynamic data that you need. But that's really key. One of the main criterion is we want to make sure that we're seeing dynamic data. In terms of what to do with the set point, so here we're kind of bumping it up sometimes, we're kind of, in the set point, we're bumping it up, we're bumping it down. There's a variety of different tests that you can do to get this data. So the kind of most common ones here are a step test, okay, where you step either the output and observe a response, or you step the set point and observe a response. That's fine. This one is really advantageous because this one can be graphically analyzed. So if by looking at this, you can figure out back to the previous section where we were talking about the first order plus dead time model. From this data, you can extract just visually the gain, the time constant, and the dead time. So that's beneficial. But at the same time, I have yet to go into a control room where they were really happy to just be like, hey, I'm going to step the output and just let it go. Is that all right? Not a ton of operators, especially for someone like me just coming in, will allow for this. So this is beneficial, and in certain cases, it's very useful. But there are other tests that are more beneficial in a production environment. So for example, a pulse test is another one that's something that I will commonly do, either with a set point bump or with an output bump, where we will pulse either the set point or the output up and then pulse it back down. We don't have to wait for it to go to steady state and come back down. We just want to see a dynamic response, and that will give us dynamic information that we can use to get those, we can understand the process, understand the model. So this is really beneficial, especially if we've got that constraint situation. So way back to the beginning of the talk, we were talking about how you want to be operating near a constraint. If you have a constraint right here, you don't want to go here, right? Maybe you're operating very closely to the constraint. You don't want to cross that line. No problem. You can bump away from it and then bump back. You won't cause any issues with failing product or throughput or things like that. You will still get the dynamic information you need. If that isn't a requirement, then generally my favorite test to perform is what is called the doublet test. So what we do is we kind of take a step test, but we sneak it in to the middle. So instead of doing a full step up and down, what we do is a half step up and then a full step down, and then we return to the starting point. So I like this test particularly for a variety of reasons. First of all, we don't deviate very much from where we're operating, so we don't cause a lot of issues in terms of production problems or in terms of disruptions upstream, downstream. Whatever disruptions we do cause, you can see that we add a little and then we also remove a little. So if you've got a tank downstream or something like that, this will help kind of average the impacts of the test. And you still get a big enough step, right? You go up by half, so you're not deviating as much, but you still get just as much dynamic information. And lastly, you get information both above and below where you're currently operating, which is generally what you're looking for when you're doing tests on data of this type or just a process of this type. So we've talked about what a good test is. We've talked about what you can do. Now, once you have that, there's still a couple things that you want to look at on the collection side. So one of the big problems we see sometimes is then getting this data back into software or Excel or whatever, things like that, or tuning packages or stuff like that. What we have sometimes is an issue with data aliasing. So what can happen, especially if you're looking at historical data, is you might not be looking at pure dynamics. So for example, here, let's say that this is coming from a flow loop. Okay, but this flow loop is being archived in some sort of plant historian. So the plant historian isn't actually storing data every second, every half second, or something like that. So you could ask the plant historian for 1 second data, and it will return 1 second points, but it will return interpolated data between the points it actually has, right? So what you might see is this situation where we have an alias data based on the sample rate, which is a problem. So perhaps we made a step, and the real process may have done something like this, nice and quick, but just because of the way the data is sampled, we don't see that dynamic information. And so when we're looking to figure out what the gain, time constant, and dead time are, we're not going to be able to get that from this data because we don't have the issue. So in these situations, you have to be careful, right? You have to understand that that's what's happening, and you may need to go to a different source for the data. Perhaps instead of the historian, you want to connect directly via OPC, or you may need to change at least temporarily change the configuration in the historian so that it's archiving more quickly, maybe on change or some sort of band kind of thing. Okay, in terms of rules of thumb for sampling, so as we talked about briefly at the beginning, the time constant of the process is a measure of how fast it responds. And we didn't go into detail about how that's derived or whatever, but basically the rules of thumb are based on the time constant. So if you have you want to sample 10 times faster than the time constant of the process. But as rules of thumb, you'll see here that for flow and pressure, those are generally fast loops. So you're going to want to be sampling them relatively quickly. Level, 1 to 5 seconds, but depending. I mean, if you have a huge tank, that can be slower, and it wouldn't have any impact. Really, the idea is that you don't want to miss anything. right? If you have a loop that has a dead time of 1 second and you're sampling every 30 seconds, you're not going to catch it. Okay, so as you can see here, the recommended sample time gets slower as the process itself gets slower, right? So if you have a distillation column that responds on the order of 5 minutes, you can sample every 30 seconds and it'll be fine, but you can't always do that. Okay. So let's talk about one last thing here, okay? So we talked about how we made an output change. You can change set point. If we're doing it in the process, just in the real world, just to kind of walk through it, okay? Here is an example of a step test being performed. Okay, you can see here we've done a doublet test with a set point change. This is a relatively smooth loop, so the noise is kind of negligible, but generally what you want to do if you're doing an automatic is you look at the noise band of the process. So you look at how noisy the process is, and then you make a step that's 3 to 5 times that, right? So that it's very clear what's the process and what's the noise. We can also see here that we have a nice sharp controller output step. So that's good. And you can see, as I mentioned before, that you can do a test either in manual mode or as we've done it here in automatic mode. But this is kind of an example of a test. Here's another one, similar deal. All right, I will pass this back to Michelle for another test your knowledge question. I will say one thing about the last one. We don't know exactly how much data the government's collecting, right? So maybe they win.
Oh, true point, Brett, true point.
From everything I've been hearing lately, I would have put TikTok on there.
The Chinese government wasn't one of the options. Anyway, sorry to interrupt. Please continue.
All right. Same deal as before. Give it a minute. Come up on your screen. Again, take your mouse. Here you can select as many as you want. What do you use for controller tuning? Step, pulse, doublet, or auto tune? So I'll give you a couple seconds to give you a chance to answer to that. All right. Okay, looks like we got almost 80% of the people in. 85. All right, I'm gonna close it down. Share the results. All right. Majority of you do a step test, then Brett's favorite, the doublet, and then the pulse, with a few of you who just don't tune in your position. All right. So with that, Brian.
Yeah, thanks, Michelle, and thanks, Brett. So far today, we've kind of talked about, what's at stake with poor control. We talked about dynamic process behavior, kind of touched on that. And then we talked about a little bit about the mountains of data and the different types of data and tests along those lines. So kind of bringing this back to process control 101. Why don't we delve into the idea of the PID itself and the different forms the controller should be used in different applications. We basically just drill this right down to proportional, integral, and derivative. If you want to go through those, Brett, and just kind of explain to us, when and where you should be looking at those, if there's a rule of thumb, things along those lines.
Sounds good. All right. So yes, so PID stands for proportional integral derivative. And so deep inside your control system, you're going to be seeing something that looks, or you wouldn't see this, but this is what it's doing. So it is looking at different parts of the error. So the error is how far away from set point you are. The proportional term is looking at what is the error right now, and that's it. The integral term is looking at the sum or the integral of the error over time. So if you're above set point, that's negative error, and so it's subtracting. If you're below set point, that's positive error, and so it's adding. And so it's just continually summing, getting bigger or smaller and making its decisions based on that. And then the derivative term is looking at the slope of the error. So you can see that these are the two predominant forms. There are a couple forms of the algorithm, but basically you can see they're doing the same thing. They just have different. So the derivative term here has one parameter. This guy has two. Here, same deal. These are mathematically equivalent. You just have to put in different numbers to get the exact same performance. As long as you know which one you're dealing with, you can get the desired performance regardless of the form you use. Okay, so as I mentioned, the proportional term, the spinning ellipse of derivative, but the proportional term is looking at how far we are right now. So it makes, depending on a given change, it will look at what is our error right now, and it will have some contribution for that. The integral term is looking at how far away we've been over time, and it's making its contributions based on that. And the derivative term is looking at the rate of change. So not whether we're above set point or below set point, just whether we're changing upwards or changing downwards and how steeply. And it's making its decisions based on that. So it doesn't care about this, but all of these three things are added together and they produce the final output from the PID controller. And by adjusting the importance of any one of these, you can get a variety of different behaviors out of the relatively simple algorithm, which is why it's such a popular way to do process control. So let's break these guys out and kind of get a better feel for what these guys are doing. So here we have what I would call a relatively well-tuned controller, okay? So we have a set point change, the controller makes a step, and then it kind of grows up to here, and we kind of get a set point response. So this is usually what we see. But what's going on underneath is kind of this interesting push and pull of a variety of different parameters to kind of get to this point. Okay, so as I mentioned, these three different terms, proportional, integral, derivative, they all are looking at error. Well, actually, in this case, we have the derivative looking at the process variable, but for now, let's just think about it like this. This is fine. You can see here that the error is an exact mirror of this space here, right? As we step up, we have a positive 10 error. And then as we approach set point, that error gets smaller and smaller as we go down, okay? So this is being fed in to the three different terms. So the proportional term is pretty much the same thing, right? It's just a multiplier. So as the error goes up, the proportional term says a lot, it cares a lot. But then as we get closer and closer to our new set point, the proportional term quiets down until it doesn't care anymore. Okay, I'm going to jump over and we can see the derivative term has a similar situation here, where as the error or the slope of the error is very strong, right? It's very steep. Right around here, the steepest it is at timestamp 50, and here, or maybe 45, we have a similar deal where as we are changing quickly downward with the error, we have a steep or a strong impact. Whoa, 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 you're changing too quickly. The derivative term is almost putting the brakes on, right? It's subtracting from what the P term is saying, okay, just because of the steepness. But you can also see that this guy, when we get to our new set point, our slope is 0, so he doesn't care anymore. So when we get to this new output at the end, what's happening is basically the I term is what's giving us our real kind of baseline that lets us handle load changes and things like that. So while it grows slowly, right, what it's doing is it's summing up this error over time and then multiplying it, right? So it's adding up, adding up, adding up, adding up, adding up. But you can see that it grows and grows and grows and grows and grows and grows until it finally gets to a new value. Okay, so these things all summed up yield this change, right? You can see we went from 40 to 50. So here we started at everybody saying 0. This guy added 10. At the end, this guy added 0. This guy added 0. So this is a really interesting thing to think about. Also, I will add that this number will keep changing until we get to set point, right? Because if a disturbance knocks us up, for example, now this error is going to go negative, which means that this I term will start to decrease, right? So this will actually be working continuously adding, subtracting to give us the new baseline that we operate on. So when you're handling load changes and things like that, the I term is very important. The P term and the D term are helpful for initial either reactions to disturbances or set point changes, but it's the I term that lets you have staying power, that lets you stay at a new set point. So these are the 3 terms. Now this is a set point change. I alluded to disturbances, so let's look at those impacts now. Okay, so, oh, I went too fast. Oops, sorry. Okay, so here we have a disturbance impact. Okay, so something knocks us away from set point downward, and our output kind of slowly works its way up until we get to a new set point. Okay, our error again is a mirror image of what we're seeing here, and we can see a very similar pattern, right? The proportional term cares, and then once we get back to set point, it's fine, it doesn't care anymore. Okay, same thing with derivative, right? But in this case, it's actually interesting because it goes in both directions, right? So because we have a steep downward slope here and a steep upward slope here, or not steep, but whatever, steep, less steep, we can see that we actually cross 0. So the derivative term is actually pushing and pulling depending on where we go, kind of adding or subtracting. But once again, it's the I term that lets us handle this load change. So we can see that because we were hit with a disturbance, our output went from 20 and wound up around 30. The I term is what let us absorb that change, find the new working output that led us to this. Now, I will also say, most of the time, unless you have a very slow process, derivative usually doesn't play a part. It usually doesn't have a very important role. Generally, if you're doing really slow processes that you need to push really hard, that's when derivative is going to come into play. But usually we're talking mostly, in most industrial applications, we're talking about just PI control. So when we're talking about tuning, if everybody wants to take a screenshot of this slide, this is the most popular slide that I present. When you're tuning manually, okay, this is very helpful to know, okay? So if we have a given process of this type, this is what happens as you increase the amount of integral action, the oomph or the push behind the integral term, okay? You wind up getting kind of more undulation, more oscillation, okay? And then this in the direction vertical is what happens when you increase the proportional action. And what you can see is kind of a similar behavior, right? There's kind of more push, there's more oomph. And so this is helpful if you're a manual tuning person, although if you're a manual tuning person, you kind of already know this, I'd say. But it also serves to highlight the difficulty when you're tuning manually, right? Because if you have something that looks like this, it's very difficult to know whether you should decrease your proportional term or whether you should decrease your integral, right? Because both of them will give you less oomph, right? So it's difficult to know where you are in this grid, but it's also, so that makes it difficult to know what you should change, which makes it kind of, you have, when you're manually tuning, you're kind of moving through all of these behaviors. One thing I will say from this is that if you, so if you see something that looks like this is the last kind of takeaway from this slide. If you see something that looks like this, where it kind of picks up, but then it really just doesn't make it to set point, what we're seeing here is not enough integral action, right? The proportional term responded well at the beginning, but then when it stopped caring as much because the error was small, the integral term just wasn't summing up fast enough, and so very slowly it finally got us to set point, right? So this is a dead giveaway if you see something that goes up relatively quickly, but then has trouble getting to the end, increasing the integral action. You get the nice pickup, and then the integral term very adeptly takes it and carries it the rest of the way, okay? So that's kind of a little bit of a primer on the different components of PID and maybe a little bit of information on PI control. Okay, so let's pass that to Michelle for, I believe, our final question.
Okay, thanks, Brett. On your toolbar, you will see a bar called questions. if you click undock pane, please type in your questions. We have, you know, an expert, a free expert on hand here, who can answer your questions for you. Also, too, just to make things a little more fun for you, and because it's Halloween, if you see handouts on your toolbar, click undock that, and we have a quiz that you can actually take for yourself, you know, or pass it around to your colleagues, have some fun at work at lunchtime. Feel free to download that. So why don't we go to the next slide and see if people will type in some questions here. Also, too, if you whip out your cell phone, snap the QR code, takes you directly to our website. On our website, we have industry-specific articles, handouts, white papers. You can sign up for future webinars. You can rewatch old webinars. It's all there available to you. All right, and then I think on the next slide, we're going to go to the final question for everybody for today. Yep. All right. So again, as you're typing your questions, I'll read those out. And you can just take your mouse. I'll leave this open a little bit. Just please have someone from Control Station contact me with more information on. We do have PID tuning workshops. They're excellent. I've taken them. They're great. World-class tuning software, control loop monitoring software and solutions, turnkey lifecycle solutions for plant reliability. That's very important these days. And evaluations based on company KPIs to meet your optimization goals at your facility. All right, so Brett, we have a question here. Does the expected response to a bump test depend on whether the process is self-regulated or integrative, example, level process?
I saw that and I expected this question. Excellent question. Yes, basically I didn't mention level loops pretty much at all. Yes, this process will be slightly different because you're right. For certain processes, that first order plus dead time equation has a specific shape. We saw that throughout these things, right? Similar to a car where when you step on the gas, you pick up kind of relatively quickly and you taper off at some new speed. A level loop doesn't act that way, right? If you have a surge tank and you have a pump out the bottom, if you step up that pump speed, the level is just going to drop and drop and drop and drop and drop. It's not going to taper out. So procedurally, we have a relatively similar procedure, okay? But the model is different. So we have a different way of understanding that type of process. But still, the PID stuff is the same, right? The P term will be looking for the error right now, and it will be making adjustments based on that. Same with derivative. Once you're back at set point, those two guys won't care. It's the integral term's job to adjust the output to get you to your working level. So the answer is yes, you would need a different model. I'd be happy to talk about that at a later date or online at a different time. But that, in terms of this, this was a 101. That would be a 102 class.
Okay, thanks, Jose. You have another question here. What is the correct way to calculate ET?
I see. Oh, I see. I see it. I see it.
Okay.
What is the correct way to calculate error? E of t. Is it set point minus measurement or measurement minus set point? So the answer is it depends. And actually, I think I might, just to make it easier for everyone, I'm going to jump back to that slide just to make it easier to talk about what I'm talking about. Here it is. Is that right? Nope. Calculate error of t. Here we go. So the question is, I'm saying this is set point minus measurement. But why am I saying it's set point minus measurement? Well, and especially if you are in a controller, if you're specifying a controller, that's how you specify. Is error set point minus measurement, measurement minus set point? The answer is it depends, just as it is with most things in control. So when we describe this one, we say, and it has to do with the controller action. So if I wanted, for example, if I had a temperature loop, When the error was bigger, I would like the output to increase, right? Or so that it would, I'm sorry, if I wanted the process to go up, I would increase my output and the process would go up, a direct acting process. In those situations, we want these numbers to be positive, right? So that when we see a positive error, which is below set point, it makes the output go up, right? So that would be set point minus measurement, and that's how it works. We could, if we had a situation like refrigeration, where we need to increase our output to decrease the temperature, there are two ways that we could make the controller do that. We could put a negative sign in front of all these things so that it would go the other way and it would push the output down. But in practice, what most manufacturers do is they just change the way they calculate error. Instead of saying it's set point minus measurement, they say it's measurement minus set point, and it essentially puts a negative sign here and a negative sign here and a negative sign here, and it makes the controller go the other way. Okay, so generally, this only is important when you start up a process, when you first commission the controller, okay? Because that's just when that's when you decide, am I opening this valve or am I closing this valve when I have an error? So you set it then, and then it's pretty much constant and you don't have to worry about it anymore. So the answer is yes, it's important, but if you set it incorrectly, it will be very obvious because the process will go the wrong way and the output will slam open or slam closed, and bad things will happen. So generally, don't change that. However it's calculated, as long as the process is kind of holding near set point, it's set correctly, and just leave it like that. But that was a fantastic question.
Okay, thanks, Brett. Thanks, Jose. Is there anyone else have a question? Brett, do you want to pull up the next slide? Oh, we do. Pull up the next slide. I'll explain this. If you should have further questions, here are your contacts. We have Damien and Kathy in Europe for Middle East and Africa, and Brian and Alessia for North America. Do you have experience with liquid level switches installed on
I see.
a liquid level?
I'll read it.
Okay.
So experience with liquid level switches installed on a liquid level bridle and how they interact with a Fisher liquid level controller and official automatic liquid level control. So yes and no. So that's a very specific question. And so what's interesting here is that from a PID specific standpoint, it's unless there's like some step change stuff or some weird kind of logic stuff, for the most part, the PID doesn't care what it's connected to, whether it's level or flow. Yeah, the difference between level and temperature, yes. But similar to how a car, a slow car or a fast car, is different but the same, it's very similar to how from a controls perspective, a flow loop and a pressure loop are different but the same, right? And so from the purposes of tuning, these procedures will generally work regardless of what you're connected to. If you make a step and you observe the response, this kind of complicated liquid control strategy or whatever will still very likely have a step response that kind of picks up quickly and then stabilizes, and you can then model that and tune based off of that. In terms of if there's extra complexity that I'm not understanding with the specific Fisher stuff, we can talk about that offline. But in terms of Controls 101, the answer is generally what the loop is connected to. Maybe it's another control loop, right? If it's the outer loop of a cascade, from the outer loop's perspective, it doesn't really matter. It sends a signal out, something happens, and then it gets a signal back in, and that's what we can model with a gain, time constant, and dead time. Then we can then generate tuning parameters based off of that. Because as far as the loop is concerned, the PID is concerned, all of that stuff that happened is just part of the process from its point of view. That's
Okay.
great questions, guys. Thank you.
All right, any more questions? We have a few more minutes. Like I said, Brett is our expert here.
I don't know. I keep answering with it depends. So
well, it always changes. It always changes.
That's right. Talk to me tomorrow. I'll give you a different answer. No,
all right. I think we're all good. if you do have a question in the future, everyone has my email address. Send it to me and I'll get it off to Brett, and he can address it from there. All right. Thanks, Dan, for a great question. With that, I think it's a wrap. Brian, thank you. Brett, excellent. Always a pleasure to do a webinar with you. Oh, we do have a question. Can we squeeze this in? Sure. Brett, what's your opinion about the Lambda tuning criteria?
So we didn't talk about that, but that's what we use basically. Yeah, lambda tuning. So what I missed was there's a link between gain, time constant, and dead time, and the tuning parameters you should use, right? So if you model the process, there are equations called tuning correlations. Again, this is not 101 stuff, but there are tuning correlations that turn those model parameters into tuning parameters, into gain, time constant, dead time. One of the more popular is what are called lambda tunings, and those actually, again, this is outside the topic, but our tuning software uses a variation of the lambda tunings called the IMC tuning correlations. That's a little bit more involved than we want to go here, but I like them. I like that they are adjustable, right? You can specify the type of response that you want. They don't box you into 10% overshoot and quarter decay or things like that. And so I like them. And go forth with your lambda tunings and tune with confidence.
Okay. It looks like Oscar Castro, did you have a question? You had your hand up. Nope. Okay, guess not. All right. Again, Brett, Brian, thank you guys. Appreciate it. Oh, no. Yep. Oh, we got to thank you. Great webinar. Thanks, Jose. With that, look for our next webinar on November 14th. We have Damian Monroe and Brad Anderson presenting for this one. So with that, thank you, everyone. Have a safe and happy Halloween.
Bye, everybody. Have a good one.
Thanks, everyone, for your time.